Okay, hi everyone. We're going to be talking about deadlocks and blocking locks. And to start off with, let's just show the problem. So you can see I've got two sessions here. One over on the left here where I'm running a couple of updates, and one on the right where I'm also running similar updates. And you can see this session on the right here is currently stuck. It's waiting because I've run the first update over here. If I go back to my first session and run the second update, it's also stuck waiting for a second or two until we hit deadlock detected, right? So those of you who've been working with databases for a while I'm sure will have encountered this at some time or another. The problem of when multiple sessions are trying to access the same resources. So we'll be looking at that in this session. Let's just stop this before we go back. So we'll roll these all back so they can continue. Alrighty then, and let's get started. So hi everyone, I'm Chris Saxon. I'm part of Gerald Wenzel's Oracle Developer Advocate team. It's my job to help you get the best out of Oracle Database and hopefully have a bit of fun whilst doing so. So it's always great to be here with these office hour session, chance for you to ask your questions. These are supposed to be kind of interactive. So please, if you're not sure about what I'm talking about or want more details, please ask away. I prefer you put questions in the Q&A window rather than the chat window. This is just a bit easier to manage and it makes it easier for other people to see. So please put questions in the Q&A window. That's enough of that. Let's get started properly. So we started off, we can see we had two sessions and we ended up with a deadlock, and the database detected this and forced one of the sessions to roll back. So why does this happen in the first place? Well, whenever you've got two or more sessions trying to change the same rows at the same time, one of them is going to be stuck. So we've got an update here and we can execute this if we start this running. If in the second session, we then try and delete that same row, well, the first session has locked that row by the update. So it will be stuck there waiting, and it's just going to sit there and wait and wait and wait forever and ever and ever until, that is, we commit or roll back that first session, that first update. So we cannot have two sessions changing the same rows at the same time. So before we kind of get into details of why this leads to deadlocks, let's just take a step back and think, well, why do we need locks at all in the first place? Why do we stop two sessions trying to change the same rows at the same time, just from general principles? Well, let's imagine we've got two sessions and they're both updating all the rows in a table. First one's going to set the values first, second one set the values to second. And let's imagine we live in a world where the databases don't lock rows whatsoever. So these can both proceed at the same time. First one will start, second one will start sometime afterwards, but before the first one finishes, and they're both changing the same rows. Well, what's going to happen here? What's going to be the result? The short answer is we don't really know, right? Just like if you've got to select a query without an order by, update doesn't impose any particular order on the rows as it changes them. It doesn't say, I'm going to update these rows first necessarily, okay? So there's no guarantee over which order the rows will change. So the first update might start from like the top of the table and work down. In theory, the second update might start from the bottom of the table and worked up. And we can end up in a situation where we end up with a big mishmash of different values in the table at the same time. And in really weird scenarios, it's always possible to kind of completely corrupt rows and they end up with a bit of a mix between what the values are in a particular column. Clearly, this is a pretty bad thing. This is something we don't want to happen. We want to avoid this happening. So databases prevent you doing this. They stop you being able to change rows in two or more sessions at the same time to prevent these kind of inconsistencies and problems in your data that can occur. So that stops things within a transaction, but that doesn't prevent all kind of anomalies that can happen. Just kind of a bit of a side step here. We live in a world where databases disallow this. So if I start updating a row and you start updating the same row, you've got to wait for me to commit or roll back. And if we've got transactions that do this, so I update a column to one value, commit it, you update that same column to a different value and commit it, well, you've just overwritten my changes, okay? So I've started, and then you've just overridden them. Whoever commits last wins, and this can lead to the lost update problem. I'm not going to talk in much more detail about this at the moment, but it's just a kind of a point here that just because the database prevents you updating the same rows at the same time doesn't mean you can avoid all types of inconsistencies and problems that can occur in your data. In general, this protects us from the worst kind of effects that can happen here, but there are still other problems that can arise even in the world that we live in where we cannot update multiple rows at the same time. So we want to avoid these kinds of data inconsistencies. But also, if we lived in a world where we could update a row and not lock anything, other weird things could happen as well. So it's not very often, but from time to time, you'll run DDL on your tables. For example, I'm running this update. What happens if you come along and decide you want to drop the table, for example? If I hadn't got some form of lock on that row and on that table, you could drop the table and my transaction could fail halfway through. Clearly, that's not very desirable either, right? So there's all sorts of weird and wonderful things that could happen if we allowed 2 or more people to change the same data at the same time. So we want to avoid it. So what are kind of common causes for this? Now, some of these, you've probably encountered many of these. Some of these might be new to you, but there's various things that can cause this. So we can get blocking locks from DML processes. So as we just saw, if you've got 2 sessions trying to update or delete the same rows, well, the second has to wait for the first to complete. And most of us who've been working with databases for a while are familiar with this kind of problem. But we can also get blocking locks on other kinds of DML actions on a table. For example, on insert. If 2 sessions try and insert the same value for the primary key or unique constraint on a table, well, they've got to wait. In order to know whether or not that value we're adding is a duplicate, does it already exist in the table, the first session has to commit or roll back for the second session to complete. Now, hopefully, this is kind of like a fairly rare occurrence in your database. Now, maybe if you like importing data from third-party sources, lots of different data sources, and there could be clashing primary keys or unique key values, you might run into this problem. In that case, you're probably looking at wanting to do like a merge type operation, insert if exists, update if not exists type thing. But in just like a general normal customer-facing application, if you've got lots of sessions trying to insert the same primary or unique constraint values, you need to look at things a bit carefully, but this can occur. Finally, one thing I want to talk about on DML blocking is when you've got foreign keys. So you've got your parent and child tables. If you delete a row from the parent table, well, the database needs to check there are no rows in the child with that parent key value. Similarly, if you insert a row in the child, the database needs to check that that parent key value actually exists in the parent table. So if you're deleting from the parent or inserting to the child, we can briefly lock those rows. We prevent the alternate action on the other table. Otherwise, again, we can end up with problems. There are some other scenarios with foreign keys that can lead to blocking scenarios. I'll cover those again in a minute. So that's DML, probably the most common scenarios here. You can also get locks or blocking locks when you run DDL, and particularly when you have DML processes and running DDL at the same time. So if I'm inserting, updating, whatever, rows to a table, and you are trying to alter that table, drop that table, a lot of forms of DDL, you'll be not allowed. You'll have to wait for my transaction to complete. Because in the general case, if you make a change to the table, it could invalidate the state of my transaction or how we're processing it and so on. So if I've got an uncommitted DML statement and you run DDL, a lot of those will be blocked. Now notice I've got non-blocking DDL. This is terminology which can be a little bit confusing because it's perhaps the opposite way to the way you think about it. If I run some DML and you run some non-blocking DDL, you have to wait for me to finish. If you run some blocking DDL, because you need to get an exclusive lock on the table, you will instantly be told that you can't get it. You have to wait for there to be no outstanding transactions. I did have an Office Hours session where I talked about this in a fair bit of detail a little while ago. So if you want to know more about that, check that session out. But principally, DDL statements can be stuck waiting for DML to complete. Finally, final one I'm going to cover at least is user locks. This is where you as a developer have explicitly asked to lock a section of code or rows in the table. That can be with the lock table statement. There's various locks we can supply there, select for update, or the DBMS lock package we can use to lock off particular blocks of code. There are some other kind of internal locks and various other scenarios that can lead to blocking situations, but these are the most common. These are the ones I'm going to kind of focus on for today. So that's a kind of a brief overview of the most common ones you're likely to run into. So as we go on, I'll see a question from Frank. Currently facing a problem with our continuous integration pipeline. During tests, we create a bunch of users on the database with different test execution sessions. When I try and get execute on a package to a technical user, I hit the ORA-060 deadlock detected. Trace file says it is waiting on a row cache lock when executing grant execute on package to each user. How can I avoid deadlock while granting privileges? I suspect the packages in the post are being compiled and is invalid when the grant occurs. I suspect you're right, Frank. I'll come back to that in a little bit later. Okay, so yeah, I think off the top of my head, I don't know exactly, but we'll walk through the process of like troubleshooting deadlocks and so on, and maybe that will help answer or help you figure out how to resolve the problem. Okay, so we'll come back to that a bit later. All right then. So there's common blocking reasons. I mentioned foreign keys, and I said I was going to talk about foreign key locking in a little bit more details. Particularly, I wanted to talk about unindexed foreign keys. So we've got our parent table and our child, and there's pointers from the child to the parent. And what we want to do is delete one of the rows from the parent. Now, this row in the parent has no matching rows in the child. There are no rows pointing to that particular row in the parent. So it's safe to delete it. Foreign key is not going to stop us. But if we've got no foreign key on no index, sorry, on the foreign key columns in the child, then how does the database know that, right? Well, it's got to go scan through the whole table, check that there are no rows in the child table with that value. And at the same time, it also has to prevent any sessions adding a new row with the value we're about to delete, or updating any existing rows the value we're about to delete, update them to that value. So even though we're deleting a row which has no match in the child, the database will still take out a full table lock. It will lock all the rows in the table briefly while we actually remove that row from the parent. So this is clearly not a great thing to happen. And I'll just jump over to a demo to kind of demonstrate how this can happen. So here we go. I've got my parent-child tables. Let's just recreate them. So we've got my parent, child, which points to that, and we'll insert a few rows. So we've got parent-child matching, and there is no row in the child table for parent ID 2, for the primary key value 2. So what I'm going to do in my first session is insert another row for the row we've already got a matching row. So ID 1 in the parent, and we're going to insert that into the child as well. In my second session, I'm going to delete the row which has no child record in the child table. So ID equals 2. Let's try that, and it's stuck, right? Why is it stuck? Well, like I say, in order to remove this, we briefly have to lock out all the rows, the entire table. But I've got a session here trying to insert something. So we can't do that, right? So this is not a good scenario. We're ending up with a situation where this delete cannot complete until this insert commits or rolls back. So if we just kind of look at what's actually going on, you can see, use the various DBA views to kind of see what's happening. We can see our session is holding it, and we look in DML locks, and here's our blocking thing. So my insert is blocking my delete on from the parent because it's trying to get this share lock on the child table. It's trying to lock the entire table. And it's not allowed to do this because we already have a lock. We're not able to do this at all. Not good. Okay, so this could lead to a lot of problems, clearly, if you ever delete rows from the parent. So let's just roll that back. We see the delete now complete in the second session. Let's roll that back in the second session as well. So we're back to where we were. So that happened because there was no index on the foreign key column in the child. Let's see what happens when we create an index. Let's create our index, and we'll insert our row into the child table again. I haven't committed it. It's just sat there waiting. I'll try and run the same delete, but you can see it now can proceed and complete. So why is it able to do that now? Well, we can now just check the index. Instead of having to check the entire table, we can go to the index on the child and say, does this value that I'm trying to remove exist in the index? Not only is that more efficient, we can just search the index for that value, but we don't need to lock out the entire table as well. So this, if you ever delete from the parent table and you've not got an index on the child table, you can end up with all sorts of problems here. So this is a question or comment from Rachel here. It is locking the child table even though you are deleting from the parent. Yes, that is exactly what was happening there. Let's repeat that again, just to show you exactly. Let's just drop the index, remove that. So let's see. You see, I'm inserting into the child, and at the moment there are no rows. Let's just check. You see, there's no rows in the child with that value. So in theory, it's safe to do that. But if I try and run this delete, because it has to lock all the rows in that table, it's not allowed to do it, right? So, oh dear, okay. Doesn't it usually create the index automatically for the foreign key? No, Rachel, there's nothing that will automatically create the index for the foreign key, okay? I mean, in some situations, this column might be part of the primary key or a unique key on this child table, in which case you'd get the index for that primary or unique constraint. But creating a foreign key does not create an index for you. So in general, no, you are not going to get an index for you, and that's in there as well. Okay, Bernard, what happens if you try and insert 22 in the parent in session 1 now? Good question. All right, so let's see that. There we go. So if I go back, we won't be able to insert 22 because it already exists, Bernard, because it's a unique constraint violation. But so we don't need to kind of worry about that. The value we've got already exists here, so we can't prevent that happening. Any other questions or comments on this before we kind of move on and kind of talk about? All right, let me just get myself out of the mess. Let's roll that back. Let's roll that back. I will create the index on it again, and just to show you again that it is now working. I've inserted into the child. It's uncommitted. I delete from the parent, and it can continue because we can check the index instead of having to scan the whole table, essentially. Okay. Alrighty then. Oh, sorry, you meant the child table. Okay, let's go back again. Let's go back. And you see, because I'm trying to drop the index and I've got the uncommitted thing here. Okay, so let's drop that index. So what you want to do is insert here, delete here, that's stuck, and now insert 22. Let me just undo that. Insert values 22. So that can continue. Interesting. Thing is, this session over here, the session on the left, has the lock on the child table, right? Session on the right is the one that's waiting for it. So we can actually still kind of manipulate the values here. And if we want to kind of, if we commit now, then we're going to get a problem because there's a child's row. We get the integrity constraint error, okay? So does that help explain what you wanted to know, Bernard? Okay, foreign key references to the primary key, we should create an index, yes. Yeah, so, okay, so you come up from Tideo as well. Some people might think that not defining the foreign key in the first place will be better, but that's a bad shortcut. Very good point, Tideo. Yes, you can avoid this problem by not creating the foreign key, but that just brings lots of other bigger problems down the line. So yes, you still need to create the foreign key. Don't think you can just drop it to get rid of this. The solution, the correct solution here, is to create the index to avoid this problem. Okay, so the question here we've got is, okay, so we saw this, do we need to go and create foreign key indexes? And the short answer is you don't actually have to create them all the time, but with a but, right? Okay. So there's three questions you're kind of going to answer here. Do you join or filter on the foreign key columns? And 90% of the time you will do here. You know, the vast majority of the time, if you've got a foreign key column in a table, you are already going to join that to the parent table, or you're just going to have a where clause that looks up particular values on that. And most of the time, you already need an index on that column for query performance, right? So a lot of times this is just a non-issue, a non-discussion, because if you didn't create that index, you know, query performance would be horrendous, and you know, people would start complaining. So you create it pretty quickly. But there are, you know, it's unusual, but you may not query it directly. Or perhaps more likely, there might be just a small number of parent values in the parent table, you know, 3 or 4 different values. They're all roughly equally likely. So the index just isn't actually that useful on the child table. That is a bit more likely, and it does occur. So most of the time, first time the answer to this question is yes, and you just create the index anyway. And because if you didn't, you'd have performance problems. Next question is, do you update primary key columns? Do you actually change the primary key value itself? Now, hopefully, I really hope the answer to this is pretty much always no, right? Because as soon as you start trying to update the primary key value, you've then got to cascade that to all the child tables. It just gets messy. It's very difficult to manage. So hopefully you almost never do that. And final question, a bit more interesting one is, well, do you actually delete rows from the parent? And a lot of databases these days, typically you don't delete anything. Like you only ever insert, and you delete things by marking them as not active or is deleted or something like that. You set a flag to mark it as deleted rather than physically actually removing it from the table with delete. So a lot of tables, it's fairly rare where you'll run a delete. So the answer here might be no, right? It might be no, that actually you never run a delete from this table. So we said, no, we don't need it for query reasons. No, we never update the primary key, and no, we never delete from the parent. The answer to all of those is no, then you can get away without creating them. And some people kind of say, you know, make sure, say, think about this. It's a myth that you need them. And while technically that is true, I prefer to take more of a kind of a risk-based approach, right? And let's say risk is basically the likelihood of something happening versus its impact. The higher either, you know, if something's low likelihood but high impact, you still want to try and avoid it, right? Something's very likely but low in impact, again, you probably want to avoid it. And it's both high, you definitely want to avoid it. So even if it's unlikely that you delete from the parent, the risk, the impact of that happening, if you ever do a delete, is really high. Let's say you've got a lookup table with some old values that you want to remove and deprecate. Someone decides to run a delete on that table. There's no matching rows in the child tables. You think it's safe, but there's no indexes on those columns. What happens? Well, you then get locks out on a whole bunch of tables in your applications, and the whole application can come grinding to a halt. So the impact here is really high if you ever need to do this. So in my opinion, although technically you probably don't need it, you should just create them. And people say, well, we want to avoid creating indexes we don't need. There's probably lower hanging fruit. There's probably bigger issues when it comes to creating unnecessary indexes, like that 5-column function-based index that no one even really knows why it exists, right? There are bigger problems when it comes to over-indexing things than creating these foreign key indexes. Personally, I think you're better off just creating them and not worrying about the risk of this happening. Okay, so I see there's some more comments and some points on this. Let's just run through them. So Rafu, foreign key may also point to a unique key that might be updated. Great point, Rafu. Foreign key can point to primary key or a unique constraint. A lot of people aren't aware of this. Personally, I think by convention, foreign keys should always point to primary keys, and you need to have a good reason to point them at a unique constraint, partly to avoid the cascading update problem I talked about. Why do we create surrogate keys? So that we can update the unique columns without having to cascade the update, but also just kind of by convention. If you've got 2, 3 unique constraints on the table, which one should we point foreign keys to? Well, if you make one of them primary, you go, well, all the foreign keys point to that. You avoid all sorts of problems there. But yes, it is a good point, Rafu. So a question from Rachel, what if the large table has many foreign key columns? You would have many indexes on the table. Yes, that's absolutely right. You would have many indexes at the table. Previously, you suggested to keep it to 5 to 7 indexes on a table. I don't recall having ever said that you would keep it to 5 to 7. You want to try and keep it to as few as you can get away with, okay? In a table with 100 columns on it, there might be 20 or 30 columns that you need indexes on for query performance reasons. So I don't think there's like a strict guideline on how many indexes you would want on a table, other than you should always ask yourself, do you need this index? Foreign key indexes are one scenario where I think the answer is just yes. The risk of getting it, if you get it wrong, the risk is too high. And business aren't going to be happy with you if there's essentially an application outage because of this. And you're like, well, yes, technically I was right. We didn't need it at the time, but things changed and so on. So there's no hard limit on how many indexes you want to have on a table. If I've said that before, then I retract that, okay? Example is a job cost detail table. You'll have to, I'm not sure what you mean by that, Rachel, so you have to explain a bit more. All right, then. So another comment from Tadeo. So hopefully no update to primary key on columns. Sadly, in the real world, many primary keys are updated, country names, for example. So it's not fair to suggest that a primary key should not be updated. Therefore, a relational model does not permit update to a unique key. It fully supports this case. Developers might not like to code additional code, but the relational model supports it. Yep, again, you're right. I think this is why we create surrogate keys, right? You have the business facing unique constraints, which could change, and then you have the internal surrogate key, which never changes. And that's kind of why we create surrogate keys, to avoid this problem with cascading updates. So yeah, one thing that you do need to watch for is there are various frameworks which can have the habit of just automatically updating every single column in the table, even if it hasn't actually changed. So it will just kind of do like, set the primary key equal to NVL, whatever the new value is, it plus itself or something. So it's a no change. And that's something you need to watch for as well, where it's not actually updating, but the framework will just auto generate updates to the primary key for you. That's something you need to watch for as well. Yep. All right, flipping through my slides there. Okay. Alrighty then, I don't see any other comments here at the moment, so let's move on and talk about deadlocks, right? Okay, so why do we have deadlocks? Well, this is when you've got 2 or more transactions trying to access the same resources at the same time. And it's what I like to call the child painting problem, right? Okay, if you are painting, there are 2 things you need. You need a paintbrush and you need some paint, okay? So you need both of those to actually be able to draw and paint your picture. So my kids, I've got 2 young girls, and they absolutely love painting. They spend a fair bit of time doing it. If you like the rainbow behind me, that's their handiwork. Okay, so they like painting, but they're still pretty young, and it's almost inevitable that at some point during their painting session, this will happen. One of them will grab their favorite paintbrush. And the other one will grab a particular color, let's say red. And they will both decide that they want what the other person has. So Rabbit over here goes, I want to paint with red, give me the red paint. And Dragon over here goes, yeah, but that's my favorite paintbrush too. Give me my favorite paintbrush, right? And so it's a bit of a standoff here. They're both holding on to one of the things they need. They're not willing to give it up, right? And they're trying to get a hold of the resource that the other one needs. So it's like deadlock. They're not willing to let go of what they've got, but they're still trying to get what the other person has. And they're still a bit too young to have properly learned like negotiation and cooperation techniques. So basically, I've got to come in and resolve the problem somehow, and tell one of them, put the paintbrush down, give it to your sister, let her do it, and swap over and that kind of thing. And it doesn't matter that there's like 5 other colors, 20 other paintbrushes. They've got to have their favorite paintbrush, and they've got to use red right now, right? And they've both got to do it at exactly the same time. So this is the problem of deadlock. We're both trying to access the same thing at the same time. So we're going to imagine this in database terms. So one of them is locking the brush in exclusive. They've got exclusive access to the brush. The other one is locking the paint, or that particular paint, and is locking in it in exclusive mode. Having done that, they both then try and get the resource that they don't have, so the brush or the paint as appropriate. Now, because the other person has it, they are both stuck waiting for the other person to let go of the other resource. But they're both unwilling to do that. They're not going to do that until they've finished painting whatever it is they actually want to do. But they can't do that because they can't get the paint or the brush that they need. Bit of a problem. So when this happens in Oracle database, the database plays the role of the parent, and it picks one of these resources, one of these statements, and does a statement level rollback. And it says, stop doing that, undo the work you've done, and then things can continue, kind of, right? So at this point, I'm going to jump back to a demo to kind of show what actually happens here. So let's see, let's get my tables here. So I've got my first one on the left here is going to lock the paint table. The second one's going to lock the brush. And then this one, second one's going to try and get access to the paint. So first person already has that, so they cannot get access. So they are stuck waiting. First, back to the first person, they kind of go, well, I want the brush. I want that my favorite brush, so I'm going to try and get it. They're stuck waiting too. And at this point, they're both trying to access the same resources at the same time. And you see, after a second or two, the database has detected this problem and forces one of these statements to roll back. So notice, now the thing here is just one of these statements that it undoes. It doesn't undo all the work. You notice my first session on the left here is still stuck waiting for the brush because the second one still has locked the brush table. The only thing that's been undone is the lock on the paint table here, okay? So this, in order to kind of get out of this properly, this second session needs to commit or roll back its resources so that the first one can actually complete and continue what it actually needs to do. So you can see if we look over here, we can see we're still actually waiting on each other. We can see my session here is blocking the other session from actually completing, okay? And if I commit, that will release the locks. At last, the first session, sorry, can actually get the lock and complete what it's doing. So let's just commit that and roll back, or commit it so it releases the locks. So this is why we have deadlock. We've got multiple sessions trying to access the same resources in a different order at the same time. So if this has happened, how do we kind of try and figure out why it happened? How do we resolve this and figure out what to do. Well, whenever the database detects a deadlock, it will create a trace file on the server. In the past, this meant you had to kind of like monkey around on the server and beg the DBA for access and so on. From 12.2, there is this handy $v$ trace file contents view, which you can use to actually read them yourself. So let's just pull one of those out. I'll just drag this over here a bit, make it a bit easier to see. And we can see there's a whole bunch of information here. So there's some interesting stuff here. As it says, the following deadlock is not an Oracle error, right? It is a deadlock due to user error in the design of the application or from issuing incorrect ad hoc SQL. This basically means it's your problem to sort out, right? So we need to figure out why it's happened. So we got our deadlock graph here. So this shows you which sessions were involved. So the X is telling us it was trying to get exclusive locks. There's different letters for different lock types, but basically they were both holding and waiting on each other. So with this session information, if you've got ASH information, active session history, or you've got other logging monitoring in place, you could trawl through and see what that's doing. But if we go a bit further down, we can see the statements that actually cause this problem. And these are actually the deadlock that I did right at the start of this session where we had the updates. We can see one session, the current SQL statement is updating that row, and in the other one, it is updating the other row. So they're both trying to update each other's rows. So now, armed with this information, you need to go through your application and say, well, what is it that actually issues this statement? Why does this happen? You see, we've got various other kind of details which might help here, things like the machine, module, and so on, to help you trace and figure it out. But basically, once you've got these statements, you then need to go through your application code and figure out why this happened. You know, what chain of events, or where in the code this happens, and what we can do to avoid this from occurring. Okay, so once deadlock has happened, pretty quickly, within a second or two usually, the database will pick one of the sessions. It will do a statement level rollback and create this trace file. We can look at this trace file to actually figure out what's going on, why it happened in the first place. Any questions or comments on that before we move on? Not seeing any other questions or comments at the moment. Just take a drink. All right. Okay, so let's move on a bit. All right, so we've had a deadlock. We can see why it's happened. We can see we've tracked down what the code is. How do we resolve the deadlock? So the database picks one of the statements and rolls it back, but at this point, one of the sessions is still holding a lock and the other is still blocked. The session has to commit or roll back to let the other one continue. So there's a couple of basic things you could do here. You could try again, basically, or just fail and tell the user something went wrong, okay? So if we try again, we'll say, if we encounter a deadlock exception, roll everything back and rerun the whole transaction. Sounds pretty good, right? Well, maybe, maybe not, okay? Remember, if we've got most of the way through the transaction, we've probably already taken a little while. You know, we've got to have acquired locks in the first place. Might have had to wait a little while for those, depending on what else is going on. We've done a fair bit of work, had to roll it all back, and then we're doing it all again. So we're taking a fair bit longer. Exactly how long will depend on your transaction and the nature of your transaction and so on. So while we can retry, this will take longer, right? It has to take longer because we're doubling the work we need to do, essentially. Or we can just give up and go straight back to the user and say, log the error, raise the exception, go back to the client, tell them something went wrong, let the client decide whether to roll back probably or commit what the work we've done, and tell the user, the customer, say, something went wrong, try again now, please, that kind of thing. So the question here is, well, which action should you do? And this is a very big, it depends, right? There is no real right answer here. It's decide which trade-off is worse for you, okay? Which is the least effective. So in an ideal world, you'd be able to retry the transaction because then it's transparent to the customer. As far as they know, nothing actually went wrong. Everything just finished, and everything's fine. Okay. So in an ideal world, you would retry the transaction. The reasons why you might not is, as I said, this could take a long time. We're running the whole transaction probably twice or nearly twice in completion. If it takes 5 seconds to run your transaction, well, we have to run that 5 seconds plus a bit of time to encounter the deadlock. So probably another second or two, roll it back a little bit there, and so on and so forth. Could take a long time to do this. It's also worth bearing in mind, I've been talking about just 2 sessions here. You can end up with very complicated deadlock scenarios where you've got like 5 or 6 or more sessions all trying to access the same resources in a weird kind of circle. If you just keep on retrying and retrying and retrying, in theory, it is possible that they just can always loop back round in a big circle and kind of infinitely access the same resources. It's pretty unlikely, but it is possible, right? So if you want to retry, you probably want to set a limit. You probably only want to retry once before you kind of give up and say, something's going on here. We need to just bail out and go on. So the time it takes to retry may be unacceptably long for a lot of customers. And the second thing is as well, what if there's a lost update? So first session, got 2 sessions, deadlock, first one rolls back, second one completes, first one tries again, we might run into the lost update problem we discussed before. A couple of things that could happen here. If you've got lost update detection, you might just end up throwing a user an error right straight back to the user anyway to tell them, you know, things have changed, fix it. If you haven't got lost update detection, then you may have corrupted your data. So it may not always be possible to retry the transaction. So what about passing it back to the user? Well, the nice thing about this is we've released all the locks, making it more likely that other sessions can continue what they're doing. The customer can see exactly the state of the data and know what they need to retry and so on. So we're starting again over from fresh. Downside of this, of course, is it's just a poor user experience. You don't want to throw errors to the user if you can avoid it, particularly if the system can recover from them itself. No one really likes using a system that throws exceptions. And particularly in some key parts of your application, this may be quite bad. Think your payment processing module. If somehow a deadlock is possible in your payment processing module and you throw an exception back to the user, that's not good. People don't like it if their payment fails, and particularly if the payment fails, but it's nothing to do with the actual payment provider, that can then cause all sorts of weird issues with, the payment providers, like, why are you trying this transaction multiple times, that kind of thing. So yeah, hopefully you're not in that scenario, but either way, there is no real good resolution here. The best solution is just to avoid it all in the first place, right? Just do not get into the scenario where we have deadlock. So how do we avoid it? Well, first thing is, ideally, at the start of the transaction, as soon as you can, you want to lock all the resources, so all the rows and all the tables that you are going to change. Reason to do this early is fail early. If something goes wrong, you can bail out straight away. You haven't done much work. But also, if you fail part way through, not only are we taking longer potentially, but in some scenarios, it just gets a bit more messy to kind of clean up, particularly if any non-transactional stuff going on in your transactions. Again, hopefully you don't, but well, old code bases, who knows what's going to happen. So lock all the resources as soon as you can. But key thing to know here is, be aware of here, is you want to lock them in the same order, okay? So this is particularly important if your transactions which are running updates or deletes against many tables. You always want to start with table 1, table 2, table 3, and so on, and every transaction locks them in that order. Otherwise, you can get in a scenario where I lock table 1, you lock table 2, I try and lock table 1, now I'm stuck, you try and lock table 2, or vice versa, and we're both stuck, right? If you always lock them in the same order, then you avoid this problem. And this particularly, you could have different transactions which need to change the same tables. And this requires coordination of your development team. You need to come up with a rule. Locking them alphabetically is probably a good one because it's simple and fairly easy to follow. But people need to be aware of this, and if they're not, you can still run into problems. You know, unrelated transactions could still deadlock each other if you're not careful. Finally, when your transaction finishes, you want to release the locks as soon as possible. So as soon as the transaction is complete, commit as soon as you can, or if there's a problem, roll back. Note, as soon as the transaction is complete. Do not start putting commits after every single statement to avoid this problem, to avoid deadlocks, because that can introduce bigger problems. You know, we've talked about lost updates. There's all sorts of other issues that can occur here. So acquire your locks early, lock resources in the same order, and complete your transactions as soon as possible. So how can we do this? Well, there's a few ways. We saw the user locks. Most common way probably is the select for update. So I've got two transactions trying to change the same rows. One of these will start, so the one on the left will win. That will start. The second one will be stuck waiting. And the first one can just continue away, do whatever it needs to do. Second one will be stuck waiting until the first one completes. And then at that point, the second transaction can actually go ahead and do whatever it is it needs to do. So that's when we're updating the same table, different, multiple rows in the same table. If we're updating many tables, like I say, you want to pick an order. Alphabetically is a good approach if you ask me, but it's entirely up to you. You as a development team, figure out how you want to do that and make sure all transactions acquire those locks in the same order. Simple, right? Well, we've got select for update here. Let's imagine we're updating 5 or 6 tables. We're going to run 5 or 6 select for updates. That could be a lot of waiting, right? We've got to run those queries, take a while. Some of them might get blocked for a little while, waiting for the resources to become free. We could spend a lot of time trying to acquire all those locks. Doesn't sound good, right? So how can we avoid this, or how can we avoid this problem? Well, a couple of techniques. You could go even more user-controlled, use DBMS lock to allocate locks. So this allows you to say section of code, only one transaction at a time can actually execute this. Sounds nice and simple. Why don't we see more of this? Well, this only locks that section of the code. We've got an update in here. Any other transaction can still lock those rows. You're still at risk of deadlock here unless you can be sure that all the code, all the changes to those tables is going to go through this code path one way or another, or use a similar approach here. So if you can make that guarantee, and it's a tricky guarantee to be able to make, you can use this. So you can just allocate one lock at the start and then continue a lock as your transaction as you normally would. But a lot of the time, this is not good enough. You will still end up in deadlock scenarios. So what about good old select for update? Well, the problem is this will just sit there waiting potentially forever, right? And basically until the other session commits or rolls back. That is not good. These days, web stateless applications, it's unlikely you'll be stuck for a long time, but it is possible. You could still be stuck waiting for a long time. Maybe there's a back-end session that didn't commit for some reason, or maybe there's some problem in the application servers holding on to these. Who knows? Point is, customers could be waiting a very, very long time. So you probably want to avoid that. Luckily, there's a few ways around this. So we could specify no wait, wait N, or skip locked. So which should we choose? Well, again, this is kind of up to you, and it depends on what your application is doing, your business rules, but kind of walk through these. So no wait, that will give up instantly. If it is not able to acquire the lock on those rows, it will just bomb out straight away. That is quite aggressive, okay, I would say. And you could end up throwing a lot of kind of spurious errors back to customers. Some scenarios you need to do that, but probably it's a little bit too aggressive in a lot of situations. Instead, you can say wait N seconds. So let's say 1 or 2 seconds. Well, how long do we pick here? It's tricky. You probably need to wait for at least as long as the transaction takes to complete. If it's a 5-second transaction, you probably need to wait at least 5 seconds just to be sure that if 2 transactions start at basically the same time, the other one's got time to finish. But 5 seconds is kind of long for a customer to wait, right? So you've got to balance off. How long are we willing to let end users wait for this versus how long is a transaction likely to have to wait for? You know, again, this is something you really have to figure out for your business and your application, how long you're willing to wait. Or you could just ignore the problem and skip the locked rows, right? You could just say, well, the rows are locked, let's just go past them and do whatever we're going to do anyway, right? This is a very specific solution, right? And it's pretty rare you want to do this because that means we're not accessing the lock. Either we'll just run into this problem later in the transaction, or we're not going to change the row. Probably not what we want. Why would we want to do that? Well, one scenario I could think of is, let's say you've got a archival process, a background process, and it deletes anything older than a year. If nobody's updated that row in a year, just remove it. We're going to copy it to the data warehouse, whatever. Keep our transactional system nice and small. But just before you run this archival process off, a customer comes along, updates one of the rows which would be deleted, sets it to the current date, so brings it to now. That background process is going to wait for this update, only to not actually change that row anyway, not delete that row anyway, because it no longer meets the criteria. So in situations like that, it can be safe, but this is pretty rare. It's kind of restartable background processes, really. So generally, for customer-facing actions, you probably want to wait like a short period of time, a couple of seconds, again, figure out for your application. Background processes, you might want to do a no wait, you might want to wait in, might want to skip locked, exactly. Depends how long, depends on what it is you want to do. So I'm going to finish up with another quick demo, and then we'll have probably time for a couple more questions before we wrap up. So I've got a table here. I've got 1,000 rows in it, and there we go. So I've got an update process, and that's going to wait a couple of seconds, select the row, and then update just that one row. Now, one of the things you'll notice I've done a bit different here. I've got my cursor, I'm fetching it and doing a where current of. Why didn't I just do the update? Well, this select for update actually runs the query, right? If we repeat this process in our update or delete, we're essentially running the query twice. Probably don't want to do that. Anyway, so let's update that one row. I've updated row 10. Then my archival process wants to delete everything with an ID less than 100. So that's the 99 rows, excluding this one. And because I've got skip locked, we can actually do that. So I'll open the cursor, I'll fetch it into an array, I'll bulk collect it, and use for all processing to run that. See, even though I'd locked the row, that will actually complete, and we've deleted all the rows except the one, this first one, execute had blocked. Just to kind of show you what would happen if for some reason I didn't do that, I did undo everything, roll back. There we go, let's update that again. If I didn't have select for update, it's now stuck. It's stuck waiting essentially forever. Probably not good. Okay, so few scenarios where you may want you do it. Yeah, from Zaza, skip locked is a way of dequeuing in a queue. I mean, yeah, you're right. That's kind of why this exists, so that a queue, advanced queuing, can actually dequeue feature rows. It is a very specific. It's very unlikely you want to use skip locked. You need to be very sure about what you're doing before going ahead with that. All right, let's just recap that quickly. So deadlock, dealing with deadlock. First thing you want to do, if it happens in your application, is figure out why it happened. And the key thing to look at here is the trace file. It'll tell you the sessions involved and the statements that caused the deadlock. So you need to inspect that, look at your code, and map that information back to your application code. It's really, we've done what we can in the database here. It's a coding application design problem. You need to resolve that. Having identified it, found the offending piece of the code, you could then start to resolve the problem, either by auto retrying transactions or just giving up and telling the user there's a problem. Both have their pros and cons, and both of them aren't great, to be honest. It's really better to just avoid this problem altogether in the first place. The key thing to do that, as I said, lock resources at the start of the transaction or as early as you can in the transaction in the same order, probably using select for update. Bearing in mind, you might want to use the modifiers. You probably don't want to just do an unqualified select for update because customers could be stuck waiting a very, very long time. Okay, so you probably want to put a no wait or a wait n in there. If you want to know a bit more about this, I've got a video talking about updates, transactions, a bit more about blocking deadlock, and Tim Hall, as always, has got an article on this that you might want to check out. We're getting close to the hour, but I've got a few minutes. If anyone's got some other questions, fire away. No other questions? No. Everyone's like, okay. Actually, we'll go back to the point Frank was saying. Yeah, Frank, I'll go back to yours. Sorry. Yeah, when you were saying the trace file saying it's row cache lock when granting execute. So you need to look and see what both sessions are doing. As you suspect, when you compile a package, you get the DDL lock on that. And that means other people cannot execute it. Now, it could also be that you are executing the code. And I forget exactly, but I think if you are executing a procedure, actually, why don't we test that? Why don't we test this out? Let's try this out very quickly. If I execute my create procedure, let's just do that. Oh no, let's just sleep that for 20 seconds. So that's going to run for a little while. Actually, let's just do it for parameter value. Yeah. So let's wait. That will sleep for 20 seconds. And in this session, let's try and grant execute on .p to u. Let's check I've got that user. Okay, I've already got that user. So let's do that. Let's execute that. And now okay, so the grant did actually execute while it would allow. I could grant while that was executing. So you'll need to look a bit more carefully about what's actually going on in the deadlock sessions there. If you've got more details, you can share them with us on Ask Tom. Don't send us the whole trace file. That breaks like confidentiality and stuff, but if you can extract out the relevant components, we could probably help you figure out what's going on there. Okay, question from Rachel. Is there anything specific to deadlocks when creating or using APIs access through ORs and Apex? Not that I'm specifically aware of. I mean, thing to note with Apex or web applications in general is that it is stateless. So you'll make the call and control will be returned to the client. This makes deadlocks or blocking problems less likely because you only hold the locks for the duration of your transaction. You go to run the transaction, go back to the database, and that resolves the problem. Or that goes back to the client, which will commit or roll back. So it makes these things less likely, but it's actually more lost updates are the problems you tend to need to look for more closely there. But just generally, if you've got transactions which update or delete the same or two or more tables, then start looking and thinking about, is this possible? And the problem is it can get very complicated because it's not just your transaction you need to look at. You need to look at all the other potential transactions. Anytime you've got two transactions trying to change the same table at the same time, you're at risk. And in big applications, figuring out exactly or why identifying this, being aware that this is a problem is an issue. Sometimes you're not aware it's an issue until it happens in production. So you need to think carefully about this. And this just generally, a lot of people don't think enough about concurrency and what happens when two or more people are changing data at the same time or at a similar time. What happens if these transactions overlap? And there's guiding principles, but generally how you actually address and resolve these issues comes down to your business rules, your application logic, what should happen if two people try and change the same things at the same time. What's your reasoning here? You know, there isn't a fixed right answer for this kind of thing. Alrighty then. In that case, I'm not seeing any other questions. We're on the hour, so I'll just say I really hope you enjoyed this. More importantly, I hope you learned something. Stay safe and hope to see you soon. Goodbye.